On the morning of September 1st, 1859, an amateur astronomer named Richard Carrington opened the dome of his private observatory outside London. He pointed his brass telescope at the clear blue sky to sketch some unusual dark spots he'd noticed on the sun. Suddenly, right over those spots, two patches of blinding white light erupted. 5 minutes later, they vanished. 17 hours later, the night sky lit up. Brilliant green and red auroras pulsed so brightly that people in the northeast United States read newspapers by their light. In the Rocky Mountains, gold miners woke up at 1 a.m. and started cooking breakfast, assuming the sun had risen. These atmospheric lights pushed as far south as Cuba and Hawaii. Down on the ground, the Victorian internet was tearing itself apart. Telegraph pylons threw sparks into the night. Operators received severe electric shocks, and in some offices, the paper used to record messages simply burst into flames. Then came the strangest anomaly of all. Operators in Boston realized the atmosphere was so heavily charged, they could unplug their machines from their batteries and still transmit messages. 2 operators held a conversation for 2 hours using only ambient electrical current. Carrington had witnessed the most massive solar storm in recorded history. In 1859, humanity's electrical infrastructure consisted of a few telegraph wires, making the damage a mere inconvenience. If that exact same storm hits our grid today, it carries a $1 trillion price tag. A solar strike hits us in 2 waves. First is the initial flash of light Carrington saw. That flash is followed by a massive physical shockwave rolling through the vacuum of space. That shockwave is called a coronal mass ejection. The sun literally hurls a billion-ton cloud of electrified, superheated plasma directly toward Earth at over 1 million miles an hour. When the plasma cloud reaches us, it violently collides with Earth's magnetosphere, compressing our protective magnetic lines inward. Under extreme pressure, billions of charged particles funnel rapidly down these compressed lines, pushing much closer to the equator. Hitting the atmosphere, they glow. A globally visible aurora is the visible friction of a violent magnetic distortion, a distortion that has direct physical consequences for metal objects sitting on the ground. To understand the danger, we have to look beneath our feet. In physics, Faraday's law of induction states that a fluctuating magnetic field will force an electric current to flow through a nearby conductor. During a geomagnetic storm, the entire crust of the Earth becomes that conductor. The storm generates what we call geomagnetically induced currents, or GICs, deep in the soil. These massive currents immediately start hunting for the path of least resistance. Usually, that path is a long, continuous copper transmission line stretching across a continent. We have hard proof of this. In March 1989, a much smaller solar storm sent induced currents rushing up into the Hydro-Quebec power grid. The extra load heated and melted massive, heavy-duty transformers, like the ones you see here. Safety relays tripped, and within seconds, 6 million people lost power. Those unplugged Victorian telegraphs functioned because a geomagnetic storm weaponizes the ground itself. It turns the Earth into a giant generator that overloads the very infrastructure designed to harvest it. Today, human survival relies entirely on a fragile, hyper-connected electrical web. A Carrington-level storm hitting that web today would destroy hundreds of extra high-voltage transformers. These are custom-built, multi-ton pieces of hardware that take months, sometimes years, to manufacture and replace. With the grid dead, the cascading failures begin immediately. High-rise apartments lose the electric pumps required to deliver drinking water. Supermarket shelves empty in days, and delivery trucks stop running as soon as gas station pumps lose the electricity needed to pull fuel from underground tanks. The collapse extends into the ocean and the sky. The electronic repeaters inside deep-sea internet cables would be fried by the voltage spikes. Up in orbit, the heated atmosphere expands, increasing drag on communication satellites and pulling them out of their orbits. While an earthquake or a hurricane levels physical buildings, a solar storm targets our technological sophistication. The more advanced and complex our grid becomes, the more vulnerable it is to the sun's reach. But we aren't completely blind. We have built defenses. Dedicated solar observatories keep a constant watch on the sun. If a massive coronal mass ejection erupts toward Earth today, scientists will see it. We will have anywhere from 17 hours to 3 days of lead time before the plasma hits. That warning window allows grid operators to purposely power down and disconnect vulnerable transformers, letting the surge pass harmlessly. Airlines can reroute polar flights to protect passengers from radiation, and operators can switch their satellites into protective safe modes. Another Carrington-level eruption is a mathematical certainty, but because we can see it coming, we can prevent a multi-trillion-dollar collapse, turning a global threat into a manageable crisis. We just have to pay attention.